A technician slides a sealed capsule the size of a small pea into an instrument. Nothing flashy happens. No lights, no flames. But that tiny capsule can reveal what your eyes can't. What's inside metal, inside rock, inside complex materials by flooding a target with neutrons. And here's the number that sounds fake until you realize what it represents. 1 gram of this material can cost more than a mansion, not because it's beautiful, not because it's rare like a gemstone, and definitely not because anyone would want to own it. It's expensive because it's not really a substance in the normal sense. It's a capability. That capsule is built around a radioisotope called californium-252, a material that behaves like a compact neutron source, the kind scientists and engineers use when they need answers that X-rays and surface tests can't reliably provide. And the paradox is what makes this story so unsettling. The amount that matters is almost invisible, milligrams, sometimes less. Yet producing it requires an industrial chain, so extreme belongs in the same category as nuclear infrastructure. So why is californium-252 so expensive? Who actually needs it? And what does a speck of it enable that nothing else can do as cleanly? If this were just a most expensive material list, it would be trivia. But californium-252 sits at the center of something modern civilization is becoming obsessed with: verification. We're entering an era where industries must prove what they built is what they claim. The right alloy in the right part, the right composition in the right batch, no hidden contamination, no quiet defects that become expensive failures later. Because the supply chains globalize, the real risk isn't only delay, it's uncertainty. Counterfeit parts, raw materials, trace impurities, hidden voids. These are the failures that break trust in high reliability systems. Energy infrastructure, aerospace, medical tech, nuclear systems, critical manufacturing. Californium-252 matters because it can enable neutron-based measurements in a compact form. Tools that can interrogate materials in ways that are fundamentally different from many common probes. And the uncomfortable part is, supply is fragile. Only a small number of specialized facilities can produce it. Production isn't fast. Scaling isn't simple. So mansion per gram isn't a flex number. It's a signal that modern industry depends on tiny, hard-to-replace measurement capabilities. Californium didn't start as an industrial product. It began as a scientific milestone. In 1950, researchers at the University of California, Berkeley reported creating a new element, californium, element 98, by bombarding target atoms and detecting a product that doesn't exist naturally in usable quantities. That was the first wow. The periodic table wasn't only something you discovered. Under the right conditions, it could be manufactured. But the turning point for our story is one isotope, californium-252. This isotope has a rare property that makes it useful as a tool. It emits neutrons through spontaneous fission, meaning some of its nuclei split on their own, releasing neutrons at a rate high enough to be useful. And that's the leap. Neutrons usually come from big infrastructure, reactors, accelerators, large facilities. CF252 offers a compact source that can be engineered into sealed capsules and inserted into instruments. At that point, californium-252 stops being an element on the periodic table. It becomes an instrument material. And the reason it costs so much is not storage. It's the production pipeline that makes it exist at all. Here's the simplest way to understand why neutrons matter. Most everyday material testing interacts heavily with electrons. Surface chemistry, electron density, near-surface behavior. Neutrons play a different game. They interact with atomic nuclei. And because they carry no electric charge, they can penetrate materials differently than charged particles do. Their interactions can produce signatures that reveal composition and structure in ways that are complementary to X-rays and other methods. That's why neutron-based techniques can be used for questions like identifying elements in a sample down to very small concentrations, in some contexts, probing hydrogen-containing materials in ways that can be difficult for X-rays, studying internal structure without simply looking at the surface. Californium-252 is useful because it gives you access to neutrons without building a neutron facility every time. But it's crucial to say this clearly. CF252's value is not the element. It's the engineered neutron source, the sealed, certified, controlled device form that can be used safely and predictably. And that packaging, shielding, certification, stability, logistics is part of the cost story. Now, let's hit the true reason the price reaches mansion levels. You can't manufacture CF252 like normal materials. You have to grow it through nuclear time. Here's the counterintuitive part. If someone handed you a full gram of californium-252 as a raw lump, it wouldn't feel like wealth. It would feel like a problem you'd need a team to manage, because its value isn't in owning it. It's in using a controlled neutron emission safely. And, in reality, most applications don't use grams. They use tiny sealed sources, milligrams or less. So why does the 1 gram cost a mansion number matter? Because it exposes what's really being sold. Not a commodity, not a luxury, an industrial capability compressed into microscopic mass. When you scale up the cost of 1 gram, you're seeing limited production capacity, slow nuclear transmutation timelines, extreme radiochemistry, constraints, and a supply chain that cannot sprint. And if that pipeline gets disrupted, maintenance shutdowns, policy changes, aging infrastructure, the ripple isn't just academic. Projects wait, costs rise, capabilities narrow. Now, let's go inside the real factory. To understand the price, imagine a manufacturing line where time is an ingredient. Californium-252 is produced through transmutation. In a high-neutron environment, certain heavy nuclei capture neutrons. After capture, beta decay can convert the nucleus into a new element. Through repeated captures and decays, you move step by step into heavier actinides until you reach californium isotopes. But 3 things make this brutal. Time. The chain isn't instantaneous. It requires long irradiation periods and decay steps you can't rush. Radioactivity. The entire process involves intensely radioactive materials, which means remote handling, shielding, and specialized hot cell chemistry. This isn't a normal lab. It's industrial radiochemistry. Separation. Irradiation produces a complex mixture. Extracting and purifying a specific isotope, especially a useful fraction of CF252, requires highly selective chemical processing. Then comes the final transformation, turning purified material into sealed sources that meet strict safety and performance requirements. So the mansion price isn't about rarity in nature. It's about the difficulty of controlled nuclear production plus precision engineering. Next, the human side. Why this capability is rare not only in equipment, but in expertise. This is a part almost nobody sees. Not because it's secret, because it's simply far from public view. Producing and packaging isotopes is a craft built around constraints most industries never face. You can't touch the material directly, you can't work fast. To meet a deadline, you can't improvise when safety margins are tight, and you can't scale by hiring 500 more people next quarter. Behind shielding, technicians use manipulator arms to perform chemistry that must be precise because errors are expensive, dangerous, and hard to correct. And the expertise itself is rare. Experienced radiochemists, isotope production engineers, source manufacturers, specialists trained over years, supported by facilities designed and licensed over decades. That's why the supply chain is fragile in a unique way. It isn't just a rare material. It's rare capability. And when a capability is rare, the market price reflects the entire ecosystem required to keep it alive. So where does it actually get used? Here's the practical payoff. Californium-252 isn't a trophy. It's used in small, controlled sources to enable specific capabilities. A few major buckets. Neutron activation analysis. Using neutrons to induce characteristic signals that can reveal elemental composition in certain contexts. Useful across research, forensics, and specialized industrial analysis. Oil and gas well logging. Measurement deep underground where you can't bring a full laboratory, and where understanding formation properties drives major operational decisions. Nuclear industry calibration and monitoring. Providing known neutron sources for detector calibration and certain startup/low power measurement contexts. Neutron radiography and specialized inspection. In some scenarios, neutrons reveal features that other methods struggle with, especially involving light elements like hydrogen. Materials research and nuclear data work. Experiments where a well-characterized neutron source is required for testing detectors, shielding, or responses. The common thread isn't cool science. It's trust. When failure is expensive or dangerous, measurement becomes strategic. CF252 helps create that measurement capability in a compact form. But it's not a perfect solution, and that's where the tension lives. If californium-252 is so valuable, why not use it everywhere? Because it comes with friction. It's radioactive. Every use involves regulation, engineering controls, transportation rules, and end-of-life handling. It decays. Over time, the source changes. Even a perfectly built source has a planning horizon. Supply is narrow. Production depends on specialized irradiation capacity and radiochemical processing lines. That's not easily duplicated, which leads to the real debate. Do we keep relying on rare isotopic sources, or replace them with engineered neutron generators? Non-isotopic neutron generation can create neutrons on demand. It can reduce some logistics and disposal burdens, but it introduces its own trade-offs: power requirements, complexity, size, maintenance, and different performance profiles. So, CF252 remains relevant because it sits in a sweet spot: compact, passive, steady. It's a benchmark that engineered alternatives must compete with. And that competition is exactly where the next breakthroughs are happening. The future isn't make a lot more CF252. The future is getting the same insight with less isotopic dependence. 3 big levers drive that: better detectors and computation. Higher sensitivity and improved analysis can extract more signal from less neutron flux, stretching the usefulness of small sources. System-level optimization. Better geometry, moderation, shielding design, and measurement workflows reduce wasted neutrons and improve signal quality. Engineered neutron generation. Compact generators and accelerator-based approaches can replace isotopic sources in many settings, trading isotope scarcity for device complexity. The honest truth is, there won't be one winner. Different industries will choose different tools based on their constraints. But CF252 will remain the reference point because it packages an unusual amount of capability into a tiny, passive source. In the next 5 years, CF252 will likely remain essential in the niches that rely on compact, passive neutron sources, while the ecosystem around measurement improves: better sensors, better models, better workflows. In 10 years, engineered neutron generation will take more territory in controlled industrial settings where power and maintenance are acceptable trade-offs. In 20 years, the biggest change may be cultural. Verification becomes a default requirement in advanced manufacturing. Inspection and authentication become as strategic as the material itself, especially as parts get more complex and supply chains demand proof. The future won't be decided only by who invents the best materials. It will be decided by who can prove what's inside them, fast and reliably. And that's why CF252 matters. It's a symbol of the measurement layer underneath the modern world. Californium-252 isn't just a rare isotope. It's connected to everything Future Forge is about: additive manufacturing and internal defect verification, advanced alloys and contamination control, composites and certification, nanotech, where trace impurities dominate performance, smart materials, where long-term measurement decides reliability. The hidden backbone of futuristic manufacturing is measurement. Neutrons, whether from isotopes or engineered sources, are part of that backbone. So the deeper lesson behind 1 gram costs a mansion is simple. The future runs on capabilities that are easy to underestimate until the day you need them. Even if you never go near a reactor, this story still affects you. Because modern life depends on trusted materials. Planes, cars, hospitals, power grids. Everything is built from parts whose properties must be verified, not assumed. As systems become more complex, the biggest risk becomes invisible. Wrong material, wrong impurity, wrong internal defect. So this is the personal takeaway. In the next decade, advantage won't belong only to people who invent new materials. It will belong to people who can validate reality, who can prove what's inside. CF252 is a reminder that some of the most important technologies are not products. They're measurement capabilities. A mansion per gram material isn't valuable because it's glamorous. It's valuable because it compresses an entire industrial capability into microscopic mass. Reactor infrastructure, radiochemistry, precision source engineering, regulation, and the need to measure the world more honestly than our senses ever can. Californium-252 is a reminder that the future doesn't arrive as a single gadget. It arrives as a chain, what we can produce, what we can verify, and what we can scale without breaking the systems that depend on it. And if there's one myth to drop, it's this: the most important materials aren't always the ones you can see. The real power materials are often invisible because they exist to make reality measurable. If you want the sequel to this story, we can go deeper into the next tier of absurdly valuable science: enriched isotopes, lab-made molecules sold in micrograms, and the bottlenecks that decide who leads the next industrial era. Subscribe if you want to stay early, because the next breakthrough won't feel like a headline at first. It'll feel like a tiny material that quietly changes what the world is capable of